Okay, welcome to note set number 9. We've already talked about multiplication of a matrix times a vector, and here we're going to set up how to look at matrix times a matrix. So it's actually very similar to what we've already seen, and this is stuff that's covered in section 2.4. And this might seem a little bit out of order since we just talked about elimination. And if you look at the next set of notes, note set 10, you'll see that we return to the concept of elimination there as well. So what's up with the matrix times matrix in the middle there? Well, in note set 10, we will see that we can interpret elimination in the context of multiplying by an elimination matrix. We'll define what that is when we get there. And to do that, to reinterpret this, multiplying and subtracting equations in terms of matrix multiplication, we kind of need to know how to do matrix multiplication in general. But there's lots of other places where you end up having to multiply one matrix times another. So this is a very general thing, and we're just sticking it in here in the middle of our discussion of elimination, just because we're kind of doing almost doing this in a way that's learning the concepts just as we need them for certain other things. So as I said, we've already looked at a matrix times a vector, and you might want to go back and revisit that before going on with the rest of this lecture. And what we're going to do here is look at a more general form. And just like we saw with matrix times a vector, there's lots of different ways to view this. And each one of those different ways of viewing it has its own purpose and uses. So sometimes we'll use one view, sometimes another view, and sometimes it helps to be able to think of all of the different views all at the same time. So we're going to look at a general matrix times matrix, and we'll look at a couple sub-cases. We'll look at the case where both of the matrices that we're multiplying are square matrices, so same number of rows as columns, so when you look at them on a page they look like a square. And then we'll look at the case where one or maybe both of the matrices are rectangular. And there's actually two different versions of rectangular. So we could have a tall matrix where we have more rows than columns, or a short matrix where we have more columns than rows. And we'll also see that this really is just a generalization of matrix times a column vector, which we've already done. And it will also allow us to look at the case of a row vector times a matrix. Now, notice that when we're doing a matrix and a column vector, the matrix has to come first, and when we're doing a row and a matrix, the row vector has to come first, and we'll see why that is. And just like we saw before, in the general case of matrix times matrix, there are cases where you have two matrices and they just cannot be multiplied. So that's a very interesting distinction from the real number case. And then we have a case where we have a row vector times a column vector, and we could also do a column vector times a row vector. So it's very important that we have some idea how to quickly visualize how all of these different cases work, and also be able to recognize cases that will not work. But the reality is that all of these cases are just special cases of the general case. So let's just illustrate what we mean by some of these different cases, or at least the different entities that enter into these cases. So we've got a square matrix, and that, in this case we're showing a 3 by 3. We've got a tall rectangular matrix. So in this case it's 5 by 3. And we're also pointing out that a column vector is just a special case of a tall rectangular matrix. And we've got a short rectangular matrix, and In this case, it's 3 by 5, and a row vector is a special case. And I'll point out that we don't always say, tall rectangular matrix. We might just say tall matrix, or we might just say short matrix. It's pretty obvious that we're talking about rectangular matrices at that point. And if we're talking about a column vector, we'll call it a column vector. It's rare that we would actually refer to that as a tall matrix. But you should keep in mind that really it is just a special case. So the first question when you have two matrices that you're thinking about multiplying is, can we even do it? Just as we saw for a matrix times a column vector, it all depends on the interactions of the inside dimensions. So we'll just use some notation here. We'll use the subscripts here to illustrate or to denote the size of the matrices, just so that we can keep track of that more easily. So A is going to be an L by M matrix, and B will be an M by N matrix, where L, M, and N are all integers. And then so with these two matrices, with these particular dimensions, we can form the product A times B. And the reason that we can do that is because if we look at the inside dimensions, so when we put them side by side in the order we want to multiply them, the inside numbers must match. So in other words, remember, this is row column. This is row column. So the first one has to have the number of columns of the first one has to be the same as the number of rows of the second one. But it's a little bit easier to just think inside dimensions must match. And then the result of the product, we haven't yet told you how to actually compute it, but before you can figure out what the numbers are, you kind of need to know what the size of the matrix that will result will be. And so if we do A times B and we see that the inside dimensions match, so we're good to go there, the result will have dimensions set by the outside dimensions, so L times N. So we'll have an L by N matrix as the result. And this is completely consistent with what we saw for matrix times a vector. We saw that A times X, the inside dimensions have to match, and we ended up getting a column vector that was L by 1 in that case. So a matrix times a column vector gives back a column vector. And we can see that this just fits into as a special case of this more general scenario of matrix times matrix. So here are some examples of allowable products. So this is allowable because we've got 4 and 4 on the inside. And we see that in this case we end up with a square matrix, 3 by 3. So this is kind of interesting. We can take a rectangular matrix times a rectangular matrix and get a square matrix out of it. Now, for this particular example, it's possible to interchange the order and we can still do multiplication. So now that's because when we interchange them, the new insides still match, so we can do the multiplication. The new outsides are now 4 by 4, so the result will be a 4 by 4 matrix. And we can already see that since those are two different size matrices, they cannot be equal to each other. So this is an interesting thing, that the order of multiplication in matrix multiplication matters. So we won't always be able to even interchange them and be able to do multiplication in both orders. But if we can interchange them, there's no guarantee that the results will be the same. And that will be true even for square times square, which will each order will give you this is doable, and each order gives you the same size result, but there's no guarantee that the results will be equal to each other. So so keep that in mind, that Matrix multiplication is not commutative, so we cannot interchange the order. There's a very specific order that, if it says A times B, you cannot switch those things around. So here's an example where we can multiply A times B, and that gives us a 3 by 5. But if we were to switch them around, the insides would now be 3 and 5. So we cannot do B times A in that case. We can't even do it, let alone ask the question of whether it's equal to A times B. And here's an example of a row vector times a matrix. Now remember, we saw that a matrix times a column vector gives a column vector, and here we see that a row vector times a matrix gives back a row vector. So this is kind of nice. We can kind of think of the matrix as a machine, and the vector is the thing that goes into it. And so if we put a column vector in from the right, we get a column vector out. And if we put a row vector in from the left, we get a row vector out of that machine. And so you can see that that we have to put a row vector to the left because we've got a matrix here that has both its dimensions, or neither of its dimensions are equal to 1. That's what makes it an honest-to-goodness matrix rather than just some special case vector. So we can't have 1 here. We have to have some number that will match with the 4. And so we can only have 1 in the first position, which means that we have 1 row. And so that makes it a row vector. So it's important to have these insights become just second nature. This is the example that we've already seen. Matrix times a column vector gives a column vector out. Excuse me. So now we know how to check to see when we can do multiplication. Now we got to find out, let me back up. We know when we can do it, and we know the size of the result when we can do it. But we need to figure out what will be the entries to go into the resulting matrix. And we'll see that there are many different ways to view that. And so really all those ways just track back to the ways that we did it for matrix times column vector. So there's a trick to find the correct size of the result. Well, I already told you one trick was to just look at the outsides, but this is more of a visual trick. So if these are the two matrices that we want to multiply, we just take the one on the right and move it up so that we're opening up a little opening here, and the size of that opening will be set by the dimensions of each of the results. So we have the same dimensions along the left, and we have the same dimensions along the top. So that just easily tells us what the resulting dimension is. So it's very easy to visualize that. But you should also be able to do it just from the, without a visualization, just checking the outside dimensions. So here we'll talk about the by hand view for doing matrix times matrix. And this is really no different than what we talked about for matrix times column vector. So I would encourage you to revisit that set of notes and compare what we're talking about here with what we had there. So here's the two matrices that we want to multiply. So the first trick is to just find the right size. So we've moved the right hand matrix up to the top, and that tells us how many columns, and the one on the left tells us how many rows. So at that point we're now good to go as far as the result. And we should also check that the inside dimensions match, and that is the case here. So we've got a 3 by 2 here, and we've got a 2 by 4. So that's good to go. Let's see. Come on. Why? There we go. Okay, so the next thing, once we've moved it up and we've created the opening of the right size, we just draw some vertical and horizontal lines that intersect at the unknown location. So I've got question marks at each location where we should have a number. And if you look at the intersection of the vertical and horizontal lines, each intersection will show you the numbers that will come into play. So for example, for this first element here, the numbers that will come into play will be the 7 and 8 on the red line, the vertical line above it, and the 1 and the 2 on the horizontal line that goes through that. So that just is a very simple way to see what numbers come into play. And how do those numbers come into play? Well, it involves inner product. So what we're going to do, we see that I've got this question mark circled here. And so as we've already said, that's going to involve the 7 and 8 and the 5 and the 6. So if we treat those as two vectors and we do the inner product between them, it would be the 7 times the 5 plus the 8 times the 6. And that's what we have down here. And so that will give you the answer for that. And likewise, this one, let me see if I can clear this off here. That went quickly. So the number that goes inside this oval that I've highlighted here would involve the 9 and the 10 and the 3 and the 4. So it's an inner product, so it's 9 times 3 plus 10 times 4 will give you that result there. So if you do all that, and I would encourage you to pause this and verify that you can complete the remaining elements in this matrix multiplication, that would be the result. And go back and look at the result that the things we did for matrix times column vector, and you'll see that this is completely consistent. We viewed it a little bit differently there, but not that much different. So really, we're kind of linking the by hand computations with the inner product view here, because they kind of work hand in hand. Okay, so some special cases of interest. Now that we know how to do all the multiplication, we should be able to think through these cases. So if we have, square times square and the dimensions allow us to multiply, we will end up with a square result. If we do matrix times column, we'll get a column. Again, the sizes have to be consistent. Now, here's an interesting one. If we do a row times a column, we get a single number, a scalar. And if you look carefully at this, this is really nothing more than inner product, right? Because of what we just said, to find the resulting element, there's going to be one element, and the resulting element would be A11 times B11 plus A21 times B12 and A31 times B13. Add all those up. So that is an inner product. So sometimes you'll see inner products written this way. And in fact, if we started off with two column vectors, say B, I'll put a line underneath it, and A, put a line underneath it, and suppose we want to do the dot product between them, we can use this idea that we just saw by saying, well, it's going to be B transpose, that makes it a row, times A. So that's a common way to write the inner product between two vectors. And that's really nothing more than this, because remember, the inner product just gives you back a scalar. All right, I suppose I should erase that so that it's not in your way there. If we do column times a row, so this is just the reverse. So when we do row times column, obviously the number of elements in each has to be the same, and we end up with a scalar, regardless of how many elements the row and column have. Here, if we do column times row, the number of elements do not have to be the same. I can have any number of elements here, and I can have any number of elements here. The inside dimensions are now 1, so this will always work. I can take any column times any row, and it will work. And what I get is a matrix, and it's kind of interesting what the result is. So if we think about drawing our lines, C11 is just going to be A11 times B11, and C12 will be A11 times B12. So every one of these numbers is just a product of two elements drawn from one from the column and one from the row, and that's it. So that's interesting, and something that crops up an awful lot. So again, if A and B are column vectors, so we have some column vector A and some column vector B, we can end up with a matrix by saying A times B transpose. And so that will give us a matrix. And remember, over here we were saying that this was B transpose times A. So it depends on, if we're limiting ourselves to writing, whenever we write A or, some letter with an underscore as a column vector, and that is what we do, we can do the inner product with B transpose times A. We can do, this is sometimes, this scenario over here is sometimes called the outer product, and so we do A times B transpose. And then we can also see the case that we've already talked about here. Come on. Come on. This is painful. I don't know why this does this. There we go. If we do a row times a matrix, we can see how that ends up giving us a row. And what we need here is the same number of elements in the row as the number of elements in a column of the matrix. And then the resulting number of elements is the number of columns in the matrix. So you need to learn to be able to think through these things quickly. It's not something that you should have to spend time thinking through. It just needs to become second nature, because we'll just rip through these results and apply them whenever necessary. Okay, so that's the kind of by hand rule with kind of an inner product interpretation built right into it. Now, if we were to write down, if we were to be going through a formal math class on this, this would be the way that the rule is first introduced, and maybe the only way that the rule is introduced. So this is the formal math rule, and it's mostly used in proofs. But you can verify that this really does nothing more than what we just said. So, let's imagine that we're going to do, some element here, maybe, C3, 4. And so now what are we going to do? So we need C3, 4 here. So I is 4, I is 3, J is 4. So this is going to be 3P and P4. And so what does that do? Let's think about this in the context of our trick. So we would be drawing a line through the third element down, and we would be drawing a line here from the fourth element over, or the fourth column over. And so what are we doing? We're taking B1, so we're going over the P equal to 1. Well, let me do it from this way. We would be taking A31, would be the element right here, and you can see that that's what we would get as the first term in this sum, times B14. That would form this first term product. Then we jump up to P equal to 2, and what does it tell us to do? We take 3, 2 times 2, 4. and so on. So you can see that this formulation is really nothing more than capturing in mathematical symbols what our by hand rule said to do. Let me clear that off. So this is just formal math notation for the by hand way of viewing it. So here's two examples. C34 and C12. So I would encourage you, even though we're not going to be using this result a lot, it's still worth knowing how to use that. So you should be able to say, from this formula, figure out what this needs to be for some given element index. So we already talked about this really in the context of the by hand trick. So really this is also just the by hand trick and the formal rule written with different notation. So I mean, this just means that these are just different views of doing the same thing. It's not multiple different things. It's just different ways of thinking about it. So the ij entry of A times B is just the row I of A dot product or inner product with the column J of B. And so that's what we're doing there. And this is an example from that. And remember, this notation here is not that they are row vectors. We're just treating the row from the first matrix and the column from the second matrix, treating them both as column matrices, and that's just a convenient notation. So again, this is just a generalization of the inner product view that we saw earlier for matrix times vector. Now, here's a powerhouse way of thinking about matrix times matrix. It's not necessarily something that we do, but it's certainly a way that we think about what does the result mean. And so each column of the product is nothing more than a linear combination of the columns of A, and in general will be some different linear combination. So let's take a look at this. So it's pretty easy to verify, and I would encourage you to try this out with a few small scale examples. We take matrix A times matrix B, assuming that they are of the right inner dimensions to allow multiplication. We can think about writing out the B matrix in terms of its columns. So we just say that, hold on just a second and I'll get rid of that. Sorry about that. So B1 is just the first column of the matrix B, all the way out to Bn is the nth column of matrix B. And what we can do is verify that if we take A and pass it through, so A times B1 will be the first column of the result, all the way out to A times Bn will be the last column of the product result. So that's easy to verify. Maybe not prove, although in a math class you would have to prove this. But here, just take a couple examples and verify that it works. But then once we have that from our previous discussion of a matrix times a column vector, giving a column vector that is just a linear combination of the columns of the matrix, we can see that each column of the product, so each one of these things and all the ones in between, is just a combination, linear combination of the columns of A. But each resulting column will be could be a slightly different linear combination because the coefficients of that combination will be different. It will be based upon the specific column of B. So as we started to show in earlier sets of notes, this idea of thinking about linear combinations is really at the heart of linear algebra. That is the machinery that that drives all the thinking. So, like I've been trying to convince you that there are doing things in linear algebra, and those are actually pretty straightforward. And to be honest, these days, most of the doing gets done with computers. But the thinking, understanding what's happening, why can it happen that way, or are there limits as to what could happen, or why is that not valid? All that thinking, which is the key to being an innovative engineer, all that thinking stuff is based upon largely this thinking about the linear combination views. So that's what's important here. So here's an example, and I'm just showing you the result for this second column here, and showing that what we can do is take this matrix and pass it through and multiply by this. That gets us, this kind of result, A times this column. But then remember that it's a linear combination of these two columns, and the weights are 9 and 10. So that's why I have a red around the 9 and a red around the 1, 3, 5. So the linear combination is going to be 9 times the first column, and then 10 times the second column. And if you work all that out, you get 29, 67, 105, which is the second column of the result. So again, this is not important necessarily as a means of how to do the computation. We've got the by hand way of doing that, or the inner product view, and the tricks are how we usually do it if we're forced to do it by hand. But this is an important insight that will help us understand why things work the way they work, how they behave, why they behave the way that they do. That's what engineers are doing. You've probably been, falsely led down a line of thinking to think that, excuse me, that what engineers do is you're given a bunch of numbers, you crunch them, and you get another number. That really is the secondary thing that engineers do. What engineers do is they try to understand, why does something work this way? And if it's not working the way that I want it to work, what do I have to do to make it work the way that I want it to work? That's engineering. And along the way, you need to boil one set of numbers down into another set of numbers and say, here is a result. But that's not the end. So in classes, you're so used to putting a box around your final number and being really proud of that final boxed-in number. That's not what engineering is doing. That's not what engineers do on a day-to-day basis. Computers do that for us. We need to know the insight. We need to know the hows and the whys. Okay, and that leads us to something that is called block-based multiplication. So sometimes we end up with a big matrix A. So here's the matrix A, and some big matrix B. And it may make sense to chop the A up into subparts and chop the B up into subparts. And often, the way, we created this big A by putting a bunch of smaller A's together. So maybe we have a bunch of subsystems that end up combining together into some bigger system. And so the big matrix A represents the big system, and all the little A's, A11, A12, are, and so on, are matrices for the smaller subsystem parts that make up the big system. And then we want to see how these two systems interact with each other. And so, fortunately, we have a simple rule for doing this. So, so what I'm showing here is this A11, that's an actual matrix in and of itself. So it's just some subset of elements within AB, so the upper left-hand corner. And what the dimensions of these are doesn't matter, but all those that are stacked here should be of the same number of columns. all those that are stacked here should be the same number of columns. Anything stacked across needs to have the same number of rows. So there are some constraints in that sense. And I'm only showing 2 stacked columns here and 2 stacked rows here, but we could have more, no reason. But this just illustrates how this works in general. So we just treat it as if it's just regular old matrix multiplication. So if we think about how we would do this if these were just number entries, we would say, well, there's going to be an element here, but now this is going to be a matrix. Its size will be set by the result of A1, B1. So we can find out, the number of columns will have the same number of columns as that, and the number of rows will have the same number of rows as those. And then they just interact just like they are regular elements. So we would have A11 times B11, and we would plus A12 times B21. And that's exactly what we have here. So the way we've set this up guarantees that A11 is multipliable times B11 and so on. So this is a result that shows up every once in a while, and it's worthwhile just keeping it in the back of your mind. So these lines that I've put in here, they're just partitioning lines. They just help us see the structure. There's nothing special about them. And that I already said. And here's another way of viewing matrix times matrix. This is just a special case of block-based multiplication. So this is largely why I just introduced that. So if we take an A and a B that are multipliable, so their inner dimensions match, and we break A down into a bunch of column vectors. Here's a typo. That shouldn't say columns. That should say rows. I'll try to fix that in the notes if I remember. And so we are partitioning B into a bunch of rows. Each one of those partitions is just a single row. If we apply the block-based multiplication, and I would encourage you to go through and do that, what we would get would be the A1 column times the B row, the one row. So we would get that. And notice that, so this is a column. This is a column times a row. That's why I wrote this as row, so that you don't think of that as a column vector. So that's actually going to give us a matrix, and it'll be L by N. And in fact, all of the terms in this will be L by N matrices that end up adding together. So this is kind of interesting. It shows us that we can interpret matrix A times matrix B as a sum of a bunch of different L by N matrices. So it's almost like breaking down this resultant product, AB, into a sum of, in this case, M different matrix components that all add together to compose or build up the result. So here's just an example of that, and we can look at the two different columns and the two different rows, and so we're going to have the red ones multiply and the blue ones multiply, and if you multiply them out, so you get this. So here's one matrix contribution, and here's another matrix contribution. You add them together, and you will get that result. So again, the illustration here is just to show you that it does work. We wouldn't really do this way necessarily, but this concept is important. So let's summarize these 6 ways that we have talked about for viewing matrix times matrix. So if you just want to do matrix times matrix, you just do the by hand trick. we have the formal math definition, which is just a math notation way of writing out the by hand trick. If you're doing proofs, which we're not doing in this course, you'd be using this a lot. But other than that, it's not terribly useful. Although it can be useful if you have to write some code to do matrix multiplication. Maybe you're working on a microprocessor and you need some code to multiply two matrices. Maybe some code already exists in a code library, but maybe it doesn't. Maybe you're the one who's helping to build that library for some new microprocessor that's being developed. So don't always think that all the tools will always be there for you. You may be the person building the tools for somebody else. So you might have to write some code to actually implement matrix multiplication. I guess I should not be on the third tip yet, or the third view. In that case, the formal math definition is precisely what you need, because it gives a very formal mathematical rule for how to compute the elements. Okay. The third view is the inner products of rows of A with columns of B. And this is certainly a handy viewpoint in some scenarios. Hey, I've got this one colored red and bold, so this is probably the big idea, that the columns of the result are linear combinations of the columns of A. And this is an extremely powerful way to visualize some of the key ideas that we'll be talking about later. We've got the block-based multiplication view, pops up sometimes, and then we have the sum of A columns times B rows, and this also shows up sometimes. So later in the course, when we talk about eigenvalue decompositions and singular value decompositions, this viewpoint, or at least a generalization of this, a little bit of a generalization of this idea, will show up, and it's kind of an interesting viewpoint. So now we need to talk about some rules of matrix addition and how it interacts with matrix multiplication. So when we add two matrices together, we just add element by element, just like we did for vector addition. And it's pretty easy to verify, since we're just doing element by element addition, that it doesn't matter what order we write things down. It'll work just fine. And the associative law works just fine. You can add B and C first and then add A, or add A and B first and then add C, either way. And if we add A and B and then multiply by a scalar, it's the same as multiplying each by a scalar first and then adding them up. So when we're doing algebraic manipulations, these are rules that come in handy to allow us to figure out how to do this. But things start getting weird when we look at the rules for matrix multiplication. Well, we've already talked about how AB is not necessarily equal to BA. It does hold in some special cases, but in general, it does not. So we can't say that this always is true. And in fact, it may not even be possible to form BA. So there may not even be a result for BA. We may have A times B is allowable, but B times A might not even be defined, let alone equal to A times B. Now, the associative law, though, is true, because we're not changing the orders of, the order in which they interact. So, like for the commutative, we're just saying which ones we do first. So we can multiply BC first, and then multiply by A out in front, or we can combine AB first and then multiply from the left into C, either one of those. Now, this assumes that the product A, B, C, that all of these are allowable to interact, so all the inside dimensions hold. And the distributive law is perfectly valid. So if I have A times a matrix sum B plus C, I can distribute A through, and it also works from the right. So if I have D plus E, I can distribute that in from the right and get DF plus EF. So again, these are things that we can use in algebraic manipulations. Scalar multiplication, I can move the scalar to anywhere I want. Doesn't affect a thing. So this was a brief introduction to matrix times matrix multiplication, and and then following up with some of the rules of matrix addition and matrix multiplication. We saw a bunch of different ways of thinking about matrix times matrix and how that degenerates into some special cases. And we talked about how some of those rules are good for actually doing the arithmetic, but the linear combination viewpoints, inner product viewpoints are essential for understanding how things work, why things work, and as engineers, if things aren't working the way we want them to work, what do we got to do to make them work? So that's what being an engineer is all about. So you really do need to grasp the concepts and not just worry about how do I get numbers to put into my pretty little box and feel proud about. You want to know the concepts. All right, so we'll see you in the next set of notes or the next video, and see you next time.